So, ladies and gentlemen, I want you to be aware that chapters 6 and 16 will be combined. Why your textbook puts two chapters that have very much in common so far apart from each other, I don't know. But they do. We're going to put them together. And chapter 6 is on thermochemistry. Thermodynamics. Anytime you see that prefix thermo, I want you to think about the word heat or energy. Okay? That's what we're talking about here. And there are, at the beginning of this chapter, a whole bunch, well, not a whole bunch, there are multiple laws of thermodynamics. And the very first one should look very similar to one that we've seen before. It says energy can be converted from one form to another, but can be neither created nor destroyed. Okay, that sounds an awful lot like the conservation of mass. This is the conservation of energy. And it's very much like the conservation of mass, okay? We're not creating energy. We're not destroying energy. It just changes forms, okay? Throw out some types of energy. There's lots of types of energy. Give me one. Okay, kinetic. What else? Nuclear. Chemical. Mechanical. Solar. Geothermal. Dark. No. It's not. Okay? Okay, but I don't know. This is not a physics class. I don't know. Alright? There's lots of types of energy. Electrical energy is another one. Alright? Pretty much every process on Earth is nothing more than changing one form of energy into another. And a very sort of large picture, almost philosophical way to say this is that the energy of the universe is constant. Okay? There is a finite amount of energy in our universe. We're not adding any, we're not taking any away, it just changes forms. Okay? Now, there are lots of types of energy. We just mentioned some of them. Primarily, in chemistry, we are going to talk about two types. Alright? Because not all types are appropriate to talk about in chemistry. And the first type is potential energy. And you hear a lot about potential energy in your physics classes. Okay? For those of you that have already completed a year of physics, you do, and correct me if I'm wrong, I felt like in my physics class we did 1,000 problems where, you know, a person throws a ball up in the air and the ball goes up and the ball comes down. Or a person pushes a car up a steep hill and the car, you know, gets over the crest of the hill and then the car comes down the hill. And there's lots of calculating potential energy, kinetic energy. Yes? Yes. Am I wrong? You do like 1,000 problems like that.
10 zillion.
Okay, thank you. Well, guys, in your physics class, you talk about potential energy in a slightly different way than we're going to talk about it in chemistry. I remember problems like, you know, a person is holding a bowling ball over the side of the Empire State Building. Calculate the potential energy of the bowling ball. Okay, I'm sure these are very useful problems in physics, but that's not how we're going to talk about potential energy in here. Okay, so I'm going to give you, this is another kind of physics example. When a dam is built and a body of water is, you know, like a man-made lake is made by putting a dam in, that water has a great deal of potential energy. When we talk about potential energy in chemistry, really, we're talking about the energy stored in chemical bonds. That's where potential energy comes into play in chemistry. And I'm giving you this example of saturated fat. Okay? Saturated fat has a bad reputation. You know, nutritionists will come on the Today Show and Good Morning America, and they talk all about how the American society is totally obese, and we're all fat, and we're all going to die of a heart attack and diabetes. Okay? And saturated fat is to blame. Rah! Okay? Well, it does have a lot of negative points health-wise, but from a purely energy standpoint, saturated fat is awesome. Okay? And whether you are aware of this or not, fat molecules are really just very, very long chains of carbon. Carbohydrates have a similar structure. Sugars have a similar structure. If you were in an English class and you had to define the word saturated, what might you say? What would you say? Full of, to the maximum, something like that? Okay. Well, tell me what this is full of. You got it. Full, meaning at every available location along this carbon chain, there is a hydrogen bonded on. I'll draw them in here. Hydrogen, 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 hydrogen. Hydrogen's everywhere. All single bonds. Unsaturated fat means it's not all single bonds, and not every available spot is occupied by a hydrogen. Okay? Give me an example of something in everyday life that has a lot of saturated fat in it. Butter. Okay, what else? Fried chicken. How about a Big Mac from McDonald's?
Everything in McDonald's.
Okay. All right. You go home. You've got a craving. You stop by McDonald's on your way home, and you get a Big Mac. And you eat the whole thing. Okay? These fat molecules are now swimming around in your stomach. And what does your stomach do to them? Breaks them down. Okay? The process of digestion on a chemical level, what are you doing to this? Breaking the bonds. Okay? You're breaking the bonds. And guys, although it does require energy to break all of these bonds, okay, what are these atoms and ions that are created? They are used to fuel processes to make, remember this from biology? ATP. You remember that? ATP is like your body's fuel. It's energy source. Anybody remember what that stands for? Sandra? Adenosine triphosphate. Okay? The energy that is stored in these bonds is used, your body will use it to do other things, like walk down the street, or pump blood through your heart, or inflate and deflate your lungs. Okay? Let's imagine that you are about to run a marathon. Good for you. Okay? Those of you that are runners, okay, Chris is going to answer this question for us. If you're about to go run a marathon, you think it's a good idea to eat a Big Mac right before? No, you're going to be barfing at like mile 1, okay? Because there's other issues with a Big Mac. But again, strictly from an energy standpoint, saturated fat is just loaded with energy. So if there weren't all these other side effects, like high cholesterol and a whole bunch of other things, eating a Big Mac would be an awesome meal right before a marathon. If it were just looking at it just from an energy standpoint. Okay? Please don't do that, by the way. Okay? Because you'll be throwing up. Well, good for you.
Good job.
The other type of energy that we're going to focus on in chemistry is kinetic, the energy of motion. This equation is an equation that gets used a lot in physics. It is on your equation sheet for this class. I'm not entirely sure why, because I've never had to use it, but it's there. What does V stand for? Velocity. Well, that makes sense. We're talking about the energy of motion, movement. But in physics, you talk about kinetic energy like the cart is rolling down the hill or the pitcher is throwing the baseball. We don't talk about kinetic energy in terms of like the atom is moving this fast at this velocity. I mean, we could, but typically we're going to talk about kinetic energy in terms of temperature. Please remember that the definition of temperature is the average kinetic energy. So why? Because all particles, all atoms, all molecules have motion. They're moving all the time. If you raise the temperature of something, what happens to these particles? They move faster. Their kinetic energy goes up. Okay? And I want you to be very clear about two words. The words temperature and heat do not mean the same thing. And people use them interchangeably, and that's not correct. Heat does not mean how hot or cold something is. Heat means energy. Okay? And energy flows or is transferred from one thing to another. And think about it. What makes sense? Do you think heat flows from something hot to cold or from something cold to hot? Hot to cold. Yeah. Okay. So I actually want you to do a little quick experiment here. Whether you're sitting in a chair or a stool, I want you to put your hand on the leg of your chair or stool. Everybody. Does it feel cold or hot?
Cold.
It feels cold. Is that because it is cold? What temperature is the leg of your chair or stool? Room temperature. Well, it doesn't feel that cold in here to me. Okay? Why does it feel cold? Okay, we are warmer. Our hands are warmer. So what? Okay, there's a transfer of heat from what to what? From our hand to the leg of the stool or the chair. And if you feel your skin right where you were just touched, put it on your face, that'll be even more, it feels cold, right? Where you just had your hand there. When your hand loses heat, whatever you're touching is going to feel cold, even if it's not necessarily cold. Because if your hand loses heat, it will feel cold. Heat flows from hot to cold. Now, some of these concepts of heat flow can get confusing, and I need to make sure you know these two terms. Okay? Whenever I use the word system, I am meaning usually a chemical reaction, whatever reaction that we are focusing on. And everything else, the room around it, you, me, maybe I'm using a thermometer. Everything else aside from that reaction is considered the surroundings. Okay? For example, we just put our hands on the leg of the chair. The leg of the chair would be the system, and we are its surroundings. Okay? So I'm going to use these terms when we talk about endo and exothermic, which we've already talked about briefly. But I want to make sure that you are crystal clear on these concepts. All right? Exothermic, heat is leaving the system or the reaction. Heat is produced, released. When we already talked about these terms when we were talking about Le Chatelier's principle. For exothermic, Do you write the word heat as a reactant or a product? Product. So endothermic, we write heat as a reactant. Heat flows into the system. All right? It's absorbed by the system. It's like a reactant. Okay? Now, we're going to have lots of questions, multiple choice and free response, where you'll be given some information and you will have to figure out whether the reaction is endo or exo. Sometimes that's very easy, sometimes that's a little tricky. Sometimes you'll be given a graph, which I'll show you in just a second. Sometimes you'll be given something like this. I want you to imagine that in my water bottle here, there's a reaction going on. And I put my hand on it, and it feels hot to the touch. What kind of reaction is happening in there? Exo. Now, this gets confusing. The system is losing heat. Heat is flowing out of the system, and where is it going? Into my hand. People get confused because they say, okay, exothermic means heat is leaving. And so in your mind, you think, okay, well, if this thing in here is losing heat, it must be getting colder. Nope. System, surroundings. We are part of the surroundings. If this thing is losing heat, it's going into my hand. It will feel hot. If I was even using a thermometer is also part of the surroundings. What would the temperature be doing on a thermometer for an exothermic reaction? It'd be going up, it'd be getting hot. Your hand is like a thermometer. Okay? So people get confused about that, and even more so when we get down here. Let me start over. If an exothermic reaction feels hot, then an endothermic reaction should feel cold. Heat is flowing into the system. Where is the heat coming from? The surroundings. My hand. If my hand is losing heat, then it's going to feel cold. Question, Chris. I'm sorry? Well, I changed the situation. So, no. We're pretending that there's a reaction in here. And the first one I said is, let's say I put my hand on it and it feels hot. That would be exothermic. If I put my hand on it and it feels cold, that would be a clue that it's endothermic. Okay? And here's another way. Oops, let me go back one. You could be presented with information. You might be given a graph and asked, is this endo or exo? Well, guys, this is an energy curve. Your reactants are always written on the left-hand side. Products are always written on the right-hand side, just like they are up here. Would you agree that this graph is generally downhill in shape? Yeah, okay. I had my reactants at a certain energy level. Heat left the system, exited, left. And here are my products. Would this feel hot or cold to your hand? It would feel hot. Heat is leaving the system. Here's my hand. It's going to feel hot. Right? When you see this general downhill shape, it's exothermic. And here is probably the most common confusion I get when people see a graph like this. They think that temperature is what's on the y-axis. That's not what's on the y-axis. People think it's temperature and they say, oh, but the temperature is falling. Shouldn't it feel cold? This isn't temperature. This is potential energy. Okay? So if my potential energy is falling, heat is leaving, it's going to feel hot. And notice what type of energy. What's the definition of temperature again? Average kinetic energy. That's not what this says. Okay? Let's make one more final connection here. I'm going to just make up some numbers to go on this y-axis. Let's say this level is 10 and this level down here is at 2. If I ask you to do a subtraction, the energy of the products minus the energy of the reactants, what do you get? -8. Do you recall last class I gave you something called a delta H value that was a way to tell if something was endo or exo? And if it was a negative number, that meant it was exo. That's where these numbers come from, is from a graph like this. Aha! Okay. Let's look at one more and then I'll stop talking. Okay. Again, reactants on the left, products on the right. Would you agree that this graph is in general uphill?
Yes.
Okay. So what's happening? Reactants are at a low level. Heat is added, absorbed, required. Whoop! Up we go to products. Would this one feel hot or cold to your hand? It would feel cold. Question?
Wait, if we're like doing some test or something, would there be the giant heat arrow, or is that
No.
just to help us now?
That's just to help you now. Question, Cole.
Okay, so if we're gonna, like, if we were to say what energy is going towards, so the potential energy is turning into kinetic energy of that.
No, there's no conversion of energy here. This is all just potential. We'll get to that later. We'll get to that later. Okay? Hold your thought on that. Alright? I'm again going to just make up some numbers here. Let's say this level is 3 and this level is 5. Energy of the products minus energy of the reactants. What do you get?
2.
Positive 2. The key is it's a positive number, which means it's endothermic. Okay, so guys, to wrap this up, not only do you need to know definitions of endo-exo, but you need to be able to interpret data like, you know, almost like in a lab setting. Like a scientist observes, you know, puts his hands on a beaker and the beaker feels cold. What type of reaction is this? Okay, endo. Or you could be shown just simply this shape of a graph. No numbers or anything, just the general uphill shape. What type of reaction is this? Endo.